Okay, things will get just slightly more complicated. Let's look at simplifying root something times root something else. The first step actually is to I find it most convenient to just take everything and combine these all together. So it's just the contents inside the first root multiplied by the contents inside the second root, all under one big old root symbol. This is actually the same formula we were just using, just in the reverse order. Normally, we had been taking a single radical and splitting it up into many separate ones that were multiplied together. But if you have separate ones that are multiplied together, you can stick all those radicals together in one big radical. The whole purpose of this is to just bring everything together first, kind of combine things and simplify some multiplication inside, and then we'll go look for those perfect squares. So you can juggle the order. I mean, there's one multiplication dot drawn in the first line of the answer step, but it's really 6 times x squared times y times 10 times x to the third times y to the seventh. They're all multiplications, even though only one multiplication dot was drawn. And because they're all multiplications, you can juggle the order in any which way you want. So I just sort of I skipped writing all the work, but 6 times 10 simplified to 60. X to the second times x to the third is x to the fifth, right? When you multiply things with the same base, you got to add the exponents. Same deal, y to the first times y to the seventh is y to the eighth. Now, this looks like the type of problem we just saw a moment ago. So here's where we look at each of the pieces and go, is that a perfect square? If so, great. And if not, let's look for the largest perfect square that is a factor. So let's just kind of look and see that 60 is not a perfect square, right? So for plain numbers, we know those perfect squares, like 49, for instance, for 7 squared, 64 for 8 squared, so 60 somewhere in between. 60 is not a perfect square. Neither is x to the fifth, because 5 is odd, right? Remember, when it's base raised to an exponent, all you're looking at is whether the exponent is even or odd. Y to the eighth, though, is actually a perfect square, so we can leave that alone. So here's how I'd like to decompose 60. It is 4 times 15. The largest factor of 60 that's a perfect square is 4. And then for x to the fifth, the largest factor that is a perfect square is x to the fourth. So x to the fourth times x to the first. It's not because 4 is a perfect square, okay? It's x to the fourth that's a perfect square simply because 4, the exponent, is even. Great. Now let's juggle the order of these things. I just personally prefer, again, it's all multiplications. I prefer to put all the things that are perfect squares in front and the things that are not perfect squares behind. In fact, I just personally like drawing a multiplication dot to separate the things in front being perfect squares and the things after being the leftovers. There's no more perfect squares in there. And then using the extended version of the true formula, you can split this up. The things that are before the dot, which were all perfect squares, I like to split those up each individually. This is a personal preference. All of the stuff that's the leftovers, in this example 15x, I just keep this all in one root. Then the root 4 and root x to the fourth and root y to the eighth, those all simplify nicely. They'll all be written in the next step without radicals because what's inside each radical is a perfect square. So you end up with 2 times x to the second times y to the fourth, all of that part no longer in radicals, times, and then now in a radical, you have root 15x. Here's another one. Root 6a squared bc cubed times root 15a to the fifth b to the fourth c to the 11th. Please be careful in reading this. Sometimes people look at that exponent of 3 on the first c inside the first radical and think that that exponent of 3 applies to the b, but it doesn't. You have to read this using the order of operations. So first, let's combine everything together. This time around, I didn't even draw a multiplication dot in between. All the things you see inside this huge radical are all being multiplied together, and I simplified the numbers part together. So 6 times 15 is 90. Otherwise, a to the second times a to the fifth. Sorry, there's a typo. This should say a to the fifth right there. Would be a to the seventh, so that at least looks corrected in that last step. B times b to the fourth is b to the fifth, and c to the third times c to the 11th is c to the 14th. Now, staring at this line that has root 90, a to the seventh, b to the fifth, c to the 14th, we should look at each of the pieces and go, is that a perfect square or not? C to the 14th is, but I think none of the other pieces are. The largest factor of 90, which is a perfect square, is 9. So we'll write 90 as 9 times 10. The 10 is part of that fluff, right? It's part of this stuff that's not the perfect square. So let's write that at the end. 8 to the 7th, we can write that as 8 to the 6th. 6 is even, so 8 to the 6th is a perfect square. 8 to the 6th times a, that a is written in that fluff area. B to the 5th has been replaced with b to the 4th times b. And c to the 14th is actually a perfect square because 14 is even, so let's just leave that over on the left. Now we'll split things up. So root 9, root a to the 6th, root b to the 4th, root c to the 14th, times, and then root the leftovers. So that is root 10ab. Then root 9 simplifies to 3, there's no radical. Root a to the 6th simplifies to a to the 3rd, no radical. Root b to the 4th becomes b squared, no radical. Root c to the 14th becomes c to the 7th, no radical, and still copy down root 10ab. Now, I tried to show a lot of steps. There's even technically, I guess, some skipped steps here, but let's say on some level many steps were shown, and later, instead of showing this answer, which is 5 lines long, you might feel comfortable just writing from the answers here, line 1 of the answer, line 2 of the answer, and then line 5. If you get there, fine. I just wanted to show some work so that if I skip too much, it might be confusing what's going on. Okay, this whole process that we have been practicing for square roots would also work for third roots or fourth roots. Again, as long as the operation inside the radical is multiplication. So let's look at cube root of 6x y to the fourth z to the 19th times cube root of 4x to the fourth y to the second. So for square roots, we had been looking for the largest perfect square, which was a factor. Now we should look for the largest perfect cube, which is a factor. So we'll take, I just recopied, since this box was getting in the way, the first line of the answer, I just recopied the question. Combined everything together here, right? So skipped a little bit more work. I hope that's okay. So this should all be stuck in one radical, a cube root. And I did the 6 times 4. I simplified the x times x to the fourth. I simplified the y to the fourth times y to the second, and so on. And now we're looking for perfect cube factors. Now 24 itself is not a perfect cube, but 24 is 8 times 3, where 8 is a perfect cube. What about x to the fifth? Well, okay, now we're looking for perfect cubes. So instead of the exponents being even, or that is multiples of 2, we need the exponents to be multiples of 3. So we can rewrite x to the fifth as x cubed times x squared. X to the sixth, well, the 6 is a multiple of 3, so we can leave that. And then z to the 19th, we're looking for the largest number that's smaller than 19, which would be a multiple of 3, and that would be 18. Okay. And then there's still one left over z. And now we split things up using the extended version of the true formula. And then each of these first things, which are all perfect cubes, will simplify with no more need to write radicals, while the cube root of 3x to the second z, there's nothing to do with that because that's all the fluff.